All right, thanks, Joe. So I'm going to be basically trying to set up why DARE is so interesting. After the break, Joe is going to be talking with some details about the technology behind DARE. So knowing that most of you are not astronomers, much less cosmologists, I'm going to spend most of the time giving some context and sort of stepping you through the dark ages and the cosmic dawn as to what we're looking for, and I'll end with sort of what we think DARE can do in particular. Okay, so this is a timeline of the history of the universe, okay, going from the Big Bang on the left over here, back here, oops, to the present day on the right side, and so that spans about 13.5 billion years, okay? And as cosmologists, at least my primary goal is to understand the history and where we got to the universe we see around us today, galaxies, stars, people, moons, whatnot. So the first step to doing that is to look around and see what the universe looks like today, and the main point that I'm going to give is that it's organized into galaxies, okay, big conglomerations of stars that are gravitationally bound together. When we look at galaxies today, the word that I would use to describe them is mature. They're generally big. They're not changing very rapidly. They are forming stars usually, but pretty slowly, and they are not interacting very closely with their neighbors. Okay, so the word again is mature, and that's the kind of picture that you should have. As the next thing we can do is look at galaxies farther away, and because of the finite speed of light, that's looking at them farther back in time. And so we're seeing them at earlier stages in their development. What we find is the galaxies are similar to what we see today, except they are generally smaller. If you look back 10 billion years or so, they're maybe an order of magnitude smaller. They are growing more rapidly. They're forming stars maybe 10 times as fast as the ones today, and they are interacting with their neighbors much more dramatically. So you can think of these as sort of teenage galaxies. It turns out that even when you look at the most distant galaxies we can see today, which are galaxies as they were about 1 billion years after the universe was created or born or whatever, they are still in that sort of same teenage category. So the next thing we can do is look very back at the early times, what's called the cosmic microwave background, which Jack mentioned briefly. At that time, which is 400,000 years after the Big Bang, there is no such thing as a galaxy. Indeed, the universe is incredibly uniform to a few parts in 100,000. Right, so we're not seeing the beginning stages of galaxies here. What we're seeing is the sort of DNA that encodes what galaxies will become. Just little tiny fluctuations that will, over the next billion years, grow into what we see today. So what we want to observe with DARE are the stages in between, which are called the dark ages and the cosmic dawn. And that's going to include the birth of galaxies, the first galaxies to form in the universe, and their childhood, growing into the sort of teenage galaxies that we see later. And the analogy with human development is actually very close, because it's during these times that the universe is going to be undergoing the most radical transformations. All right, two things that I want to highlight. It's the first time that complex structures emerge in the universe, most likely in the form of individual stars. And then those individual stars, it turns out, are very exotic. They're not like the stars we see in any of the galaxies around us today, or even the distant teenage ones. They are qualitatively different. Okay, they're hundreds of times bigger. They destroy themselves in this sort of suicidal phase transition. But we have never seen them. They're just theoretical pictures right now. Okay, so what we need to do is explore this era. And it turns out, of course, that's a very difficult era to explore. It hasn't been done yet. Actually nowhere close. They will observe, sort of make tentative steps into this era, but we really need a transformational new kind of way of looking at the universe to really see back. And the way we want to do this with the DARE mission is with a spin-flip transition of neutral hydrogen. So this is when the proton and electron spins flip. That leads to a very small change in energy, which produces a photon of wavelength 21 centimeters. Now, as that photon travels through the expanding universe, that wavelength also expands, and so when we see it, it's going to have a wavelength of a few meters or so. Okay. The nice thing is that because the final wavelength depends on how much expansion has taken place, and so basically how long the photon has been traveling through the universe, each observed wavelength that we see corresponds to a different initial point for the photon. So what DARE is going to be doing is taking a spectrum of the sky in this transition and seeing basically each observed frequency or wavelength is going to correspond to a different time, and so we're going to be mapping out this entire history of the cosmic dark ages and this cosmic dawn that ends them. And so this is the key figure that we show to illustrate what we're going to be looking at. Down on the bottom axis here is the observed frequency. So lower frequency means longer wavelength, means more expansion, means emitted at an earlier time. So the earliest times in the universe's history are over here on the left side of the diagram. And as I step through the physics here, I'm going to show more of this diagram as to what's happening. So the dark ages themselves are sort of refer to the era before the first stars formed. And so there's not much going on in the universe. And if you map out what this spin flip background is going to look like, there's not much happening either. So that y-axis is showing the brightness of this signal, which we measure in temperature units for reasons that you don't need to understand. 0 means there's going to be no signal. Negative temperature means we're seeing an absorption against the cosmic microwave background, and positive means we're seeing it in emission. So during the dark ages, we see faint absorption, but actually that absorption goes away, and by 100 billion years or so after the Big Bang, there's actually no signal whatsoever. But that's about the time that the first stars in the history of the universe form. And those first stars turn on this spin flip background through a process that's analogous to fluorescence. Okay, so this picture is showing some fluorescent makeup. If you look at it in visible light, you don't see anything. But if you shine a UV light on it, those UV photons accelerate the molecules excite the molecules. As the electrons decay, they decay through visible transitions, and so you see a glow. Right? And that's analogous to what the first stars do to the spin flip background. The ultraviolet photons excite the atoms. As those atoms decay then, they emit or absorb 21 centimeter spin flip photons, I should say. Okay, so if we look at this plot of what the universe is doing in this transition, once the first stars turn on, we go from having 0 signal to a very strong absorption signal. Look at this solid line here. That's the fiducial model I'll talk about. Okay, and so as the first stars turn on, you turn on this spin flip background. And so we can see that exact moment when those first stars turn on. Soon after the first stars form, the first black holes will also form. The black holes will attract the matter around it. That will fall in at high velocities. It will collide, heat, and emit high energy radiation. Those X-rays will then be able to travel through the universe and heat the gas to very high temperatures. Right? And as far as the spin flip signal is concerned, we go from a very cold universe, which is absorbing. As these X-rays heat the universe, they turn that cold gas into hot gas, which turns absorption into emission. And so by looking at this era, we're learning about the first black holes to form in the universe. Okay, once those black holes and stars are in place, they also produce photons that ionize neutral hydrogen. And when you ionize the hydrogen, you strip off the electron and you get no more spin flip background. So this is a very important phase transition in the history of the universe for understanding subsequent generations of star formation. And it's kind of what we think of as the end of this cosmic dawn. This movie is showing a computer simulation of what this reionization process would look like in the spin flip signal. The color scale is the brightness of the spin flip background. And the black blobs are the ionized bubbles that are growing up around the first stars in the universe. And eventually they fill all of space and you have no more signal. Okay. All right, so because you're getting rid of all the neutral hydrogen, this reionization takes your emitting signal and it puts it back towards 0 as you destroy all of that neutral gas again. Okay, so what we want to do with DARE is actually measure what this spectrum looks like. What I'm showing here is, of course, a theoretical prediction of it. Right, and we're really looking to isolate a few key physical facts. And they're encoded in where the sort of turning points of this signal, all right, the sort of dramatic changes in what's going on with it. And we've lettered these. The first one, A, is out here, and we won't be able to observe that. The DARE window is between these vertical dashed lines here. Okay, so turning point B is when you're going from no signal to strong absorption because of the fluorescence process from these ultraviolet photons from the first stars. So this is telling us sort of precisely when those first stars formed. The rate at which it then declines is basically telling us how they're growing and filling the universe. It turns out they kind of self-regulate themselves. So the problem, of course, is that as a theoretical predictions, we have no understanding of what this really looks like to sort of orders of magnitude. So the other curves on this diagram are showing other plausible models for what this signal will look like. And you can see that there are pretty dramatic sort of order of magnitude differences in the signal that we're looking for. The next turning point is down here when the universe goes from decreasing temperature or stronger absorption to increasing temperature, and that's when these first black holes form and kick in. So the turning point right here is telling us when those black holes appear, and then basically the rate that it increases is telling you how black holes grow. Now we know in the present universe that black holes basically are very closely related to the galaxies that they live in. Okay, so and we presume the same is true at high redshift at early times, and so this rate is telling us sort of the relationship between black hole growth and galaxy growth. And then finally, this last turning point D up here, is when you go from this heating by the black holes to this reionization process where you're getting rid of all of that neutral gas. So that right here is telling you when this reionization point began. That's really significant for those of us who worry about these early galaxies, because that's sort of a transformational event in the phase of the intergalactic medium. And that intergalactic medium, the material between the galaxies, is the fuel out of which all galaxies form. And so ionizing it directly affects how future generations of galaxies will form. All right, so last thing I want to show is how well we think DARE can do. So this is a similar model to what I just showed. This is the brightness of the universe, of the spin-flip background as a function of observed frequency. I believe in this, the solid blue is the input model. Okay, the dot dashed black is how well we think we can recover that from DARE, and then the dotted curves out here, which hopefully those of you at least in the front can see, are the sort of 1 sigma confidence intervals around that. So you see that we actually recover this spectrum pretty well. The right-hand plot is showing quantitatively how well we can constrain the locations and amplitudes of these turning points. This one here, and this one here. All right, so the first star's turning point, it turns out we can't do real well on. That's sort of at the edge of our band, and it's also the hardest one to sort of clearly distinguish. But still, we get its location within a few megahertz. The other two we get very, very precisely. So this first black hole transition, the one down here, we get to within a megahertz or so. And reionization is a little bit better than that. Right? So we can really pin down when these fundamental transformations in the constants of the universe took place. And this is unique. No other mission currently planned, whether it be JWST or a 30-meter ground-based telescope or something, can really get back even beyond sort of this point right here. Okay, so I'll end there. I hope I've convinced you that this is a really important and interesting area to study. And that DARE has a unique capability to sort of fill in when these important transformations are occurring.
We certainly have time for a question or two.
So I'm going to play devil's advocate. Don't get me wrong, this isn't a criticism. I think this is fantastic. You must assume a certain cosmology to, let me ask it differently. How sensitive are your templates, your models, to your choice of cosmology? And what sensitivity do you have to probe not just those 3 turning point areas, but details of cosmology that could impact the results? And related to that, could you be fooled by exotic processes, dark matter decay or something like that, if something new popped up like dark energy or whatever, how would that impact this?
Okay, so the first question is how much do I trust the curves that I've shown, and not at all is the answer. And I think everybody on the team agrees with that. This is completely unexplored territory. We have theoretical models. Whenever theory exists in isolation, it's useless, and I'm a theorist. So I don't trust the models, but I think that it sort of parameterizes what we think we can learn. And what we will actually learn is probably different and even more interesting. As far as exotic processes and whether this can really be used to probe cosmology, basically the amplitude of this signal is a calorimeter. It depends precisely on the temperature of the universe. And so if you have any exotic process that affects the temperature of the universe, this probe is basically a calorimeter of that process. So decay of primordial black holes, decay of dark matter annihilation, cosmic string, mergers and decay. All of those things, people have written papers and shown that it substantially affects the signal. Now, if we see a much different signal than this, can we uniquely say which one of those it is? Absolutely not. But it tells us there's something exotic going on, which I think would be much more interesting than the astrophysics.
Right now assumes the standard.
Yes, absolutely. So, and first, a specific thing, this turnover right here, you see that in these different models that I said these are very, very different models of structure formation, but this turnover right here really doesn't change much. And that's basically depending on the amplitude of the primordial power spectrum that we think we get from inflation. So this is a probe, in some way of a specific process in the early universes.
One other quick question?
Can you tell if supermassive black holes are primordial?
We'll be able to tell from DARE. Not directly. So this formation of the first black holes, there are a couple of different ways it could happen. One is through remnants of basically star formation. Another is the direct collapse of big globs of gas into supermassive black holes. So both of those would give similar overall pictures here. I'm not sure how much of the differences we could dig out. If there were black holes that existed much earlier, if they are small black holes, then they will decay and they will affect the temperature that we're seeing right here. If they are big black holes, then basically they'll have no effect on what I'm talking about right here.
With that, I think we need to close this first half of the session. I believe Steve is certainly around and could answer additional questions.